Okay, we're good to go.
Perfect. Well, most of you should know Kevin and I at this point if you have attended any of our previous training sessions. But just quickly, my name is Morgan Cherney. I'm the South Central Territory Manager supporting Texas, Oklahoma, Arkansas, Kansas, and Missouri. So I'm sure that I've met you guys previously. I know I was there a couple months ago doing some training courses in person as well. But today, Kevin Peary's, our application engineer, is going to be doing an advanced OTDR setup and troubleshooting class. Like Kevin mentioned, it's going to be super open forum. So if you have any questions, feel free to unmute yourself and just ask as we go along. But Kevin, I'll kick it off to you.
Good deal. Thank you very much. Again, my name is Kevin Peary's. Like I said, a lot of you have probably sat in on some of my training. This one's going to be a little bit more in depth. And so, there's an assumption there's basic understanding for OTDR. So we'll get into some of the advanced setup, really dialing down the importance of pulse width and, looking at ways to do precise fault isolation and stuff like that. And so, it'll be a combination of this whiteboard kind of setup that I do along with some VNC. And so we'll push some buttons and test network and, kind of run through it. And so basically, just like with any of the training that I've done, I always talk a little bit about, kind of the fiber fundamentals. And so this is the fiber 101 stuff, right? So just very, very, very high level, because, you've probably sat through this a few times with me, but just as a refresher for about 10 minutes here, we'll talk about the importance of, understanding what index of refraction is, what total internal reflection is. Eventually we'll get into mode field diameter mismatch, which is really important to understand, particularly if you're splicing from bend insensitive fiber to say standard single mode fiber. And you might see something like that coming out of, say, a switch or a hub, where you might have a product like CMOD from CommScope, which is kind of that pre-terminated modular FDP that they have inside the switch or the hub. Since it's pre-terminated, it has a tail coming out there that runs out, say, into your volt or into the street that splices into your feeder fiber that comes in, an 864, a 1728, whatever fiber you have feeding that hub. And so we'll talk about the mismatch of that mode field diameter between those two different types of fibers, what it looks like, that kind of stuff. And so we'll jump right into this drawing that, a lot of you have seen that, that I do, which is basically talking about total internal reflection. And again, I'm going to spend just a couple of minutes on this just to tie in the conversation. But as you know, basically fiber, we inject light at a specific angle and it reflects off of the cladding, right? This is basically what we do. Anytime there is a change in material type, there's going to be reflection. And so that is light that basically bounces back towards a transmitter, right? That bounces back towards a transmitter. And so reflection is really something that is, that troubled me. So most of my career when I was on the backbone side, so I used to work for a company that maintained long haul fibers along the right of way of the railroad, very similar to, the organization that you're in. And so one of the biggest issues that I had when I was, a route tech was, driving X amount of miles to go clean a connector, right? So connector cleanliness was a huge issue, and what was causing that was reflection. And so we'll talk about reflection, how to troubleshoot with an OTDR, how they merge, how they, give you blind spots and those types of things. But from a fiber 101 perspective, we care about that. So, coming back to total internal reflection, basically we bounce light off of the cladding. And so it just reflects off the cladding, and it has to hit this particular spot here to reflect. One analogy I like to give is, if you look at a surface of a water, right? You look at the surface of a water, and if you're standing on the surface of that water over here, looking down into the water at a very specific angle, if you look at the water, you can see basically the reflection of the sun. You can see the trees and all that kind of stuff. This is total internal reflection. So that one little section of that water turns into basically a mirror finish or reflective mirror finish, right? And so that's what's happening with our fiber. I've talked about that, many times on my fiber 101 stuff, but this is total internal reflection. It's important for us to maintain the geometry of the glass, to maintain that, that the light stays in there, because, excuse me, if you don't, then that light will escape. So if you pinch the fiber too much, that light will escape out into the cladding. and out through the coating, and then it'll shine through, right? That's what happens when you bend a fiber and put a VFL on there. You have that red light. And so that's basic, kind of total internal reflection. Anywhere where there's an air gap, like this UPC connector here, anywhere where there's an air gap, you're going to have reflection, right? And so anytime there's a change in material, and what I mean by change in material is, this particular glass might be SMF28, right? Or, to be precise, G.652 is what they call it, G.652D, or the different classifications. SMF28 is just a Corning name. So that's this specific type of glass. It will have its own index of refraction. And so when we talk about index of refraction, we're talking about IOR. And this is an important setting inside the OTDR for precise fault isolation. Index of refraction is basically the speed of light within that specific material. So the baseline is 1.0. So the index of refraction of 1.0 is the speed of light within a vacuum. So this is the speed of light in space, 300,000 kilometers per second. That's the speed of light in space. As soon as, that light enters the Earth's atmosphere. So you have this light coming in. As soon as that light enters the Earth's atmosphere, it'll come in at a specific angle. But as soon as it hits, comes into the Earth's atmosphere, it's going to slow down because now it's going through a different material type. And so the index of refraction is going to change. So out here in space, you might have, you'll have 1.0 index of refraction. As soon as it enters the atmosphere of Earth, it's going to slow down because now it's traveling through air. So it's going to have some sort of resistance to it, right? So the index of refraction will start to go up, to whatever it happens to be. And then as soon as it enters through water or fiber, it'll have a different index of refraction. So index of refraction is very important to understand if you're going to do precise fault isolation. And so you'll adjust this. You'll adjust this based on the fiber type or the material type. In our unit, when we go through the setup, I'll talk about it. But in our unit, our default setting for index of refraction is basically G.652D fiber, which is standard single mode fiber, right? There's going to be a different index of refraction for different types of fiber. So if you're doing long haul fiber, you might have something like Leaf. You might have True Wave. And again, these are brand names. I'm using these because this is typically what, the naming that you would use in the field, right? People don't say G.652D. Now they'll say SMF28. They'll say things like All Wave, Leaf, True Wave. I mean, there's a lot of different types of fibers. These are the brand names. But basically, when you're looking at these types of fibers, they are deployed throughout your network for different reasons. Leaf fiber, they call it large effective area fiber, is really good for dense DWDM, long haul transmission, really deep DWDM stuff. So is, True Wave as well. And so there's different vintages. I mean, there's different types: slope, reduced slope, negative, positive dispersion. There's all, and we're getting more into advanced optics on that. But the point of this one is that these will have different index of refraction. So if you pull up the white paper specs on these, it'll have that information in there. So you can go to Corning.com, Prismium.com, whatever company is making your fiber, and then look that up, and it'll tell you the index of refraction. And plugging in that index of refraction, which I'll show you when we get to the OTDR setup portion, will help you do that precise fault isolation. And so again, index of refraction is the speed of light within the glass. And the reason why it's an important setting, because if you know the speed of light within SMF28, and you know the OTDR, half a millisecond to get to the end and back, you know how fast it's going, you know how long it took, that gives you distance, right? If you know you're going 60 miles an hour and you drove 2 hours, then you went 120 miles. This is what index of refraction allows you to do. It allows you to adjust for that so you can, more precisely find your fault. And so this is the, basic, this basic fiber concept of total internal reflection, index of refraction. When you're dealing with the different end face types, this is important to understand because on the advanced OTDR side, having a deeper understanding for fiber really allows you to interpret your OTDR traces better. So now you're getting the more advanced. So we'll talk about not just advanced setup, but advanced interpretation. And so different types of end faces will have different reflective and loss properties. For most of the fibers that you're dealing with, whether it's UPC or APC over here, right? These fibers here are the two primary end phase types that you're dealing with today. UPC is probably most of your network. You're starting to see APC from your perspective. You're seeing APC out in the field with your OptiTip connectors and whatnot. If you're doing any sort of fiber to the home, which I'm sure nobody on this call is doing, then you might see more APCs. The difference between UPC and APC is the end phase, right? So there's LC UPC, SC UPC. So there's different connector housing types, but the end phase type primarily is UPC and APC for your environment. And from a loss perspective, when we look at this from a loss perspective, going across the connector, we're seeing typically 0.5 dB or better, right? So your specifications, I think, get down to like 0.35, 0.45. Typical is about 0.2, 0.3. But on the average, we usually, when we're talking in generalities, 0.5 dB or better. Reflection-wise, we're talking about reflection. Reflection is light that bounces back towards the transmitter. This is what causes your bit errors. This is what causes dribbling errors, right? This is displayed in a negative value. And for UPC, we're looking at -50 to -55 dB of reflection. This is light coming back. And this negative number is kind of it's really a ratio. It's a percentage of light coming back. In open, so if I have an open cleaved or UPC connector, an open flat connector is -14.7 dB. And this is important to understand because when we get into our advanced interpretation of choices, this number will start making sense to us, right? An open UPC, open meaning there's nothing plugged into it, is about a -14.7. So that's the reflection coming off of that. And again, reflection is incredibly important. In fact, most of you know, especially if you chase dribbling errors. So when I was in field ops, I used to work for Quest for years and years. I actually started in construction, putting in fiber for MCI and the original Quest, SP Construction, SP Telecom, years ago on the rail plow. And basically, when I was a technician, I used to spend a lot of time when I was on the operations side chasing dribbling errors. So typically when we go to a site that's taking errors, you'll get a call from the test center or the NOC saying, hey, you're taking dribbling errors at this particular, remote amp site. You drive out there. The first thing you do is you get out your power meter. You get out your power meter and you unplug the fiber from the receive card and you plug it into the power meter, and then you read light levels. And your light levels will say, hey, I'm getting -15 dBm. And for most systems, -15 dBm is pretty decent light, right? Depending on the receiver sensitivity. So what do? You clean fiber and you plug it back in. You're not cleaning fiber to improve the power. You're cleaning fiber to improve the reflection, right? And unfortunately, power meters don't read reflection. They only read power, right? And if you compare it to water pressure or water in general, pressure, PSI, water pressure is loss. The quality of that water is reflection, right? So you can have good water pressure, but that doesn't necessarily mean the quality of your water or the taste of your water is very good. And so it's important to understand these two different aspects, because when you look at a system, this is two of the big critical parameters when you're doing fiber characterization, right? The two of the critical parameters, meaning what is my loss across the span and what is my ORL across the span? And so what contributes to loss in ORL? Well, high splices, high connectors, high attenuation within the fiber. And an OTDR will help you find that stuff. An OTDR IOLM will help you find that stuff. What contributes to ORL? To a very, very, very large degree, connectors, right? Connectors. I have a diagram. I'll have to find it one day and put it in the presentation. But most ORL, or total span reflection, that's what ORL is, right? It's total span reflection. After a certain amount of distance, fiber doesn't, the fiber doesn't contribute. Fiber itself intrinsically doesn't contribute much to ORL after a certain distance. So in a very short distance, in a very short distance of fiber, let's say this is a fiber that runs across, and these numbers are probably not precise because I don't remember what it was. So we'll say 1 kilometer, 10 kilometers, 30 kilometers. And again, these numbers are probably not precise because I have to look it up, but I really want to get the concept across. Fiber intrinsically, so the glass itself, contributes to reflection or ORL because there's scattering within it, right? And so if you're to plug in a fiber, say a 1 kilometer fiber, and measure the ORL, it's going to be very high. It's going to be 45 dB ORL. But as that fiber gets longer and longer, this number is going to drop and drop and drop. But at some point, it hits somewhere around the mid-30s, and it doesn't drop anymore. The fiber can be 1,000 miles long, and it'll still be 35 or better. The main reason why is because the glass is getting so long that if there is reflection here from the glass, it's too weak to come back. And that's what we need for reflection. So fiber contributes only so much ORL. Then eventually it just flattens and it remains that number until infinity. And it's somewhere in the mid-30s to high 30s. I'll have to look it up, and in the follow-up email, I'll find that chart and send it to you. That way you have something more accurate than my conceptual drawing here. But what does contribute to ORL? What contributes to ORL is when you start adding connectors. 1 connector, 2 connectors. And when you start adding connectors to the system, these start to contribute ORL. So all of a sudden you have these connectors here, and it only takes one. It only takes one connector to break the system. This one is neg 50. This one is neg 50. This one is neg 40. Now all of a sudden this neg 40 causes additional reflection. So now your ORL up to this distance is going to be different. It's going to be, say, 32 or whatever. And so connectors contribute greatly to ORL, and the best way to troubleshoot a connector and the quality of a connector is with an OTDR IOLM device. And so that's what we'll be talking about today. So UPC connectors, expect between neg 50 and neg 55. APC connectors, the loss is going to be the same, but expect between neg 60 to neg 65 dB of reflection. So when we do the advanced interpretation, this will make more sense to you. And the reason why, if you sat through my class, you've known it, as the reflection comes in, anytime there's a change in material type, we're going to have reflection. But because we have an 8-degree cleave here, it's going to come back at a different angle. It's like bouncing a ball off a wall, and one wall's flat, one wall's got an angle on it. The return angle of the path of the ball is going to be different. So if you look at these two different end faces, one's going to have much more of a steep angle or a wider angle, and it's not going to hit that nice little, blue, that mirror finish over here. It's going to hit over here to the left, and then it's going to bleed off into the cladding or run along the cladding here, right? And so APC connectors have less reflection because they change the angle of the return path, so it doesn't come back as efficiently. And that's the entire reason why. This is why when a fiber is broken, it kind of rounds off, right? We've all seen it on an OTDR trace, and I'll draw it when we have the OTDR trace. But when you look at an OTDR trace and you have the launch and whatnot, if it rounds off like this, when I was in field ops doing troubleshooting, if I saw something round off, that usually meant that I had an open. Or it was plugged into something absorbing light. Basically, I wasn't getting a nice cleaved finish from an open. And so it was indicative of a broken or shattered fiber. So this is the total internal reflection part that I'd like to talk about. I don't want to get too much more deeper into that because I have whole sessions on Fiber 101, so we don't need to get into that in general. So I want to get make a shift over and taking some of this information now, tying it into OTDRs. And we're talking specifically about OTDRs because, when it comes to the tools that we have OTDR and IOLM. IOLM is kind of our advanced OTDR. So it does a lot of this thinking for you. So it's really important to understand that, with an OTDR, there's a fair amount more of expertise involved. And, since I've been in telecom in 91, but I probably started running not a backhoe, but an OTDR late 90s on a regular basis. And of course, they've made a big shift since then, the old Tech Rangers, the CMA 4000s, all these different OTDRs over the years. And so, the actual troubleshooting and the use of them haven't changed tremendously. It's just the quality of it and, the amount of noise and whatnot, and the precision has changed, quite fundamentally. So when we're looking at an OTDR, what does an OTDR do? An OTDR sends out a pulse of light. It sends out a pulse of light. So you basically have a fiber here. So in fact, let me go to a different screen here so I'm not drawing on this one. So essentially it sends out a pulse of light and interprets the backscatter. And so this pulse of light comes out. You know, of course it's bouncing and whatnot, but basically it sounds out a pulse of light. Anytime there's some sort of discontinuity or change in material type, it's going to change the way that the backscatter comes back. And then we'll detect that on the OTDR, and then it will display that in a certain manner. If it's a connector, it's going to display it as a spike because there's reflection, right? And so when you look at this means to me reflection. If it's just a splice, then you're going to see just a drop without reflection. And so this is important to understand. So when you're looking at fibers or the OTDR trace itself, you know, and you're looking at this, you know, you're looking at this launch. So it might look something like this. And so this is, we'll say this is a high level OTDR trace, right? So when we look at this, what does this tell me? Well, we know this is the launch here. So this right here is the launch because that's zero footage, right? And if I'm using a launch cable, which you should be, you should always use a launch cable. We'll talk about that. And so I have this spike here. This spike tells me that I have reflection because that's what reflection looks like. You know, the OTDR pulse hits that air gap. It reflects back. It spikes up. That's reflection, right? So that tells me there's reflection. This is my launch cable. So this is my FDP, basically. And then I see a drop here. So I got a drop. So this tells me that this is a non-reflective, meaning there's no reflective. So we'll say non-reflective. In a non-reflective event is typically a splice, could be a pinch, non-reflective loss. Because you can see that it drops down, right? So it comes in here and it kind of just, it drops down. So this is loss. And if you look at an OTDR graph, and we'll point it out later, if I were to zoom into this reflection, it looks like this. So that is the symbol on an OTDR for reflection. This is a symbol on an OTDR for non-reflective loss. So this is typically a splice. So it has loss, but no reflection. No detectable reflection. Same thing with this one here. This one's a little bit different. See how it goes up? This is also non-reflective, but this is not a loss, it's a gainer. And we'll talk about that from low field diameter mismatch. And so this is a gainer, and a gainer looks like this on the OTDR event table. This means that there is a gain in power here. So I'll have like a negative 0.2 dB. And we'll talk about this a lot because you'll see this a lot in your transition from the hub over to the feeder fiber, in the field. This is a non-reflective gainer, gain in power. And this, of course, anytime you have a gainer on the left, you're going to have a loser on the right. So this is an exaggerated loss. So this might be 0.3. And we'll talk about this more in detail later. So for troubleshooting purposes, when I see something like this, it's incredibly important to know your network. So I'm going to say, okay, so this is my FDP over here. Then I have this splice that's on that one corner. Then I have this other splice on that other corner. Oh, and over here at this particular location at, 30 kilometers. So this is at 30 kilometers. At 30 kilometers, you know what? That's where we go aerial. Yeah, we go aerial for a couple of kilometers there and come back down. And so this portion right here is aerial fiber. So that tells us that there's a change of fiber type, at least from OSP to aerial cable. And so there might be a mode field diameter mismatch. They can be the exact same type of fiber, SMF 28, G.652. They just have different vintages. And so I used to like doing troubleshooting like this, like, this section, that's that one aerial section. There's that change in fiber types. And so that's, kind of some of the advanced OTDR stuff that we're talking about that we kind of try to tie in, right? We try to tie that information in. So that's what an OTDR does. It sends out a pulse of light and it interprets that backscatter. So now when we draw this OTDR trace, we understand kind of what we're looking at. We understand this a little bit more, what this means. And from the perspective of this is power and this is distance. So this is distance here. And this is basically your power. And the two settings that control that, what controls power is going to be setting your pulse width. And we'll talk a lot about that. And then setting your distance, of course, is your range. And so we'll talk about that, which just leaves the last one for averaging time or time in general. So that's your actual, high level from an OTDR. So if we take that and then kind of, relate that to an OTDR trace. So I have let's see here. I have a VNC in here. So I have an FDB1 with a 730C in it. And this one's a combo unit, so it's modular. Right now I have the OLTS on one side and I have the OTDR IOLM on the other. So I'm going to fire up OTDR. So essentially in my office, I have about 4 launch cables plugged into each other. Most of them are 150 meters. I have a 500 meter, I believe. And then I have like 1,000 meter or 2,000 or 5,000 meter. I can't remember what it was. We'll find out here in a second. All plugged in together. And I also have about 10 feet of bend insensitive jumper in between, just to show it to you. So this is the main screen on an OTDR right here. So this is the main screen. Range here, over to the left, this is range. Range controls the display range. So if I set it 5 kilometers, this is going to change to 5 kilometers. This is the display range. This is incredibly important. So if let me shoot a trace real quick so we have something to look at. So I'm just going to shoot a quick trace only at 1550 so we have something to look at for 5 seconds. And I'm going to do an auto test and we'll come back to this setup. I just want to have a graph up here and have some settings up. And so I'm just going to auto to 5 seconds. I know some of you rolling your eyes. Auto, you got to be kidding me. And so let me show you what the OTDR did, right? And so looking at this, the distance was set to 5 kilometers, which means we're 5 kilometers out to here. That's our display range. The display range is incredibly important. The longer the range, the further this display range goes, obviously. But you want to make sure that the end of fiber here is closer to here as possible, right? You don't want it way down over here. You don't want the end of fiber to be over here because what's going to happen is the OTDR times the pulse based on the range. So if you're set the range for 40 kilometers, but you're only testing 10, you're going to get some possible echoing because the timing of the pulses will be off because we're timing it based on distance. And so in this case, I set it for 5 kilometers. Could we have gotten away with 2 kilometers or 2.5? Maybe, but not really, because if you look at it, 2.5 is too close to the noise floor. So if I were to go in here again and set it for 2.5 manually and then retest it, it'll fill up the display range, which is great, but the noise floor you don't see enough of the noise floor. So with our OTDR, we have a 5 dB noise floor. So if you notice here, the noise floor is about 5 dB. This is our noise, which is really, really good, right? But the downside is to this is, you see this come down into the noise, but you don't know if it comes back up because it was just a high loss. And so you really need to make sure that you see enough of the noise to know that, it's bottomed out. It's not going to come back to life because that can happen. I've seen it more than a few times. And so in this case here, 2.5 was too little, 5 was too much. The good news is with our OTDR, so over here to the bottom right, here is this button. Is this button right here. Hit that button there, and you can actually edit the ranges. So normally what I do is I click the highest one. There's no way that you're doing 400 kilometers with any OTDR. And so you click on 400 kilometers, and then a little window should pop up, like a keyboard to edit it. Now, of course, I got VNC plugged in, so my VNC is probably overriding it. But let me go ahead and put something in there. Let me put a 3.5 in there, 3.5 kilometer. Then I hit OK. So now you look on the display, I have a 3.5. So now I can use that. So this is really good if you're doing kind of the front haul side, closer to the front haul side of testing, or the access side. So if you're only testing 2-3 kilometers, or if you're doing network extension drops or anything like that, very short distances, you can add your own range. We see this a lot in fiber to the home, where they'll get in there and put in, half a kilometer and stuff like that. So now I have a 3.5. So if I were to do another test, I'm going to have a much more optimized view here. I'm going to have a 3.5 kilometer view. And now you can see it fills up more of the display. Oops, I didn't set it right. You know, I have a setting in here that's not resetting it. But basically, what's going to happen? Oh, there it is. It's set to 3.5. So now we're set for 3.5. So now we take up more of the display range. I could have even used 3 kilometers if I wanted to. So that's one thing you can do to customize your OTDR is to get into this option here. And depending on the age of our OTDR, we're going to have it in all of them. This is where it's at for the newer versions, you know, over the last 5 years. But get in here and create your own custom distances. You know, you're never going to test 260 kilometers, so add something else in there. You know, add something else in between. You know the different ranges. You can do the same thing for duration, but I don't see that near as often. And so now I have that one custom range in there. So that's what range is pretty much, you know, how far can I test? And, you know, as far as my display range. Pulse width and duration, though, incredibly important. Pulse width and duration are, pulse width is power, but also resolution. Duration is averaging time. And so to give you an idea of what pulse width does, pulse width is one of the most important settings on an OTDR. It really is. And so what happens with an OTDR is, you know, let's say we're looking at a standard front haul network here. So this is a standard front haul network, very similar to some of the stuff that you're looking at today, right? Where over here to the left, you have the hub, you have your volt, and then of course you have all your splices in between, however many splices, and then you have your handhold. So you have 2 handholds over here. The first handhold is usually your DMARC. The second handhold is DMARC of, say, a wireless provider. But this is, you know, say a typical mid-haul, front haul setup that we see today. And so what pulse width allows us to do, in fact, I got a better one here. What pulse width allows us to do is, so this is basically like a cheap overlay of an OTDR. Here's what pulse width allows you to do. It allows you to go in there and you shoot a pulse of light, right? You shoot a pulse of light. And let's say that I'm shooting 5 nanoseconds. Here's what 5 nanoseconds would look like on an OTDR trace. So essentially, what we're doing is we're going to have our launch, never volt, splice, 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 splice. Actually, connectors. These two are connectors. This one's a connector, and this one's probably a connector. And then, you know, we have our end, whatever, right? So this is what we're looking at on a standard trace here. And let's say that this was shot at 10 nanoseconds. 10 nanoseconds is a very short pulse width. So what does pulse width mean? An OTDR, as I mentioned before, sends out a pulse of light, and it sends it out measured in time. So a 5 nanosecond pulse width means the laser turns on and bursts for 5 seconds and turns off. 5 nanoseconds rather. So it's very, very fast. So we're talking about, you know, very, very fast signal. So you're bursting really, really fast. So which is a lot of sampling because each pulse is sampling the fiber, right? That's 10 nanoseconds. It's 5 nanoseconds. But as you bump that up, you know, all of a sudden you're testing 100 nanoseconds. Now it's much longer. The longer the pulse width, the more power, the further you could test. And so as you increase your pulse width, you can test further and further and further, but you lose spatial resolution. Spatial resolution is the ability to measure close events, very close events, 2 very close splices, 2 very close connectors within a tie cable, those types of things, right? And in a long haul network, if you're testing 100 kilometers, you know, roughly 60 miles, you're using a super long pulse width. That's, you know, over 1,000 feet long, you know, in pulse, right? It's really, really long. And the pulse is your resolution. And so that's your sampling. And what that means is at 10 nanoseconds, I am sampling the fiber a lot so I can see every single event here. But the downside to that is 10 nanoseconds is very weak. So after, say, you know, we'll say after 10 miles or so, it drops off into the noise. So now we're not seeing everything. We're not seeing past these 2 splices here mid-span. So what do? We increase the pulse width to 100 nanos, you know, to 30 nanoseconds. So now we can test further, right? We can test further with 30 nanoseconds. 30 nanoseconds allows us to test here. So we go to 100 nanoseconds. So 100 nanoseconds allows us to test the entire span. And so this is essentially what pulse width is allowing us to do. As you increase your pulse width, you can see further and further, but at the expense of spatial resolution. At the expense of spatial resolution. And so what I mean by that is, if we were to look at, these different events here, 10 nanoseconds, because it's a very short pulse width, it is going to see the vault that is 100 feet outside of your building. It's going to see both of these splices, but it's not going to see any of this because it doesn't have enough power, right? That's what 10 nanoseconds allows you to do. 100 nanoseconds allows you to see possibly the vault splice, but not necessarily, because it's kind of close because it's only 100 feet away, right? So it might merge these together, where now you're going to have just one big launch. And within that pulse, within that event, it's going to be the FTB panel and the vault splice mixed in together, because 100 nanoseconds is a very long pulse. So 10 nanoseconds is about a meter, right? I believe so. Yeah, it's about a meter. So 100 nanoseconds is 10 meters. And that's the length of the pulse. So if I have an event that's more than 10 meters apart, or about 30 feet, then I'm not gonna be able to pull. And so that's why when you're doing fiber characterization, you do a front panel shot, and then you do a short shot, they call it as well, and a span shot, right? Those are the two big things that we do. And so 100 nanoseconds merges those two together. It might merge these two together into one big loss, but it will see all the way to the end. And so that's the problem with pulse width. As you increase the pulse width, you'll get more distance out of it, but you sacrifice resolution. Can I see two events that are close together, or does it merge it? So if these two splices here were, say, 15 meters apart, right? If they're, say, 15 meters apart, at 10 nanoseconds, I would see it, because at 10 nanoseconds, I got 1 meter resolution. At 100 nanoseconds, I got about 10 meter resolution. So I should be able to still tear them apart. But if I go higher, 275 nanosecond, then it'll just merge it. And what it's going to do is it's going to take the first splice, which is, let's say 0.1. It'll take the second splice, which is 0.3, and merge them together into one event. You will not know which is which. This was a big issue when I was doing hot cuts or when I was doing fiber restoration. So somebody comes out there to the railroad right away, or to your running line or whatever, and they put an auger into your cable. So they put an auger into your cable. And so one of the downsides of that, of course, was, and all of a sudden I got a broken fiber. And, typically what we try to do in a situation like that is we try to pull slack, right? So in this instance here, let's say that we had a cut fiber right here. Let's say right about here, right? But a cut fiber there, and I'll zoom in for that because we don't need to see the rest of it. And we try to pull slack and we can't. If we can't pull slack, then you'll go and get a section throw cable. When I was a tech, we used to stage fibers that were about 100 feet long with splice cases already terminated on both ends. So they're already prepped, and the bare fibers laying in the tray. So that way we only had to prep the cable in the ground and just slap it into our splices. So it really reduced our MTTR, right? And so what would happen is all of a sudden now we got, this section throw in here with two splices. You have one splice here, one splice here, and this is only 100 feet. Shooting an OTDR trace from the left, I could see both splices, right? I can measure both splices and see exactly what they are. But from the other direction, because it's so far away, we'll say, 40 kilometers, it's going to come in and it's going to only see one splice. And this one splice is going to be these two merged together, because the pulse width coming from this way was 275 nanoseconds. The pulse width coming from this way was 10 nanoseconds, because it's an outage. I don't need to see over here. I only care about my break. So I can drop my pulse width down just to see my break. And so that's what was happening in this instance here. So that's why pulse width is very important to understand, because as you increase your pulse width, you'll get more distance, but you'll sacrifice resolution. So what you can see. And a good point to that right here is, I'm going to do one test at 5 nanoseconds. I'm going to increase the averaging time. I'm only going to do one wavelength, and I'm going to show you some close-up event. So 5 nanoseconds is a very short pulse width. but it will not go very far. So if you're testing from hub to hub, you know, you're not going to be able to get to the far end if the hubs are, say, 20 kilometers or more out. So in this case here, I'm shooting about 2 kilometers of fiber inside my office. So over here to the left, way over here to the left, you'll see event number 2. So event number 2, what I'm going to do is I'm going to scroll up here on my event table. I'm going to select event number 2. So there's event number 2 highlighted. While it's highlighted, I'll hit this button over here. This button here. This button means zoom, snap, and set your markers to the highlighted event. So it's going to zoom, snap into that highlighted event, and set the markers that it used to measure that event. So I'm going to click it. Here we are. We're zoomed in. It's zoomed into that event. And so this is, if you look at the distance here, 0.15 meters. So about 150 meters, right? So 500 and some feet. So 500 and some feet out, I have reflection. I know what I'm testing. So I mentioned the importance of knowing what you're testing. I know what I'm testing. And essentially, this right here is regular fiber, G.652D or SMF28, standard single mode fiber. This fiber here is standard single mode fiber. This here is that one 10-meter jumper I told you about. That's bend-in sensitive jump. And so this is simulating what we call a mode field mismatch. And a mode field diameter mismatch, for the interpretation purposes here, mode field diameter mismatch is essentially when you splice 2 dissimilar cores together. They have slightly different mode field diameter. This is exaggerated here. So this over here is, say, G.652D fiber, SMF28. And this over here, this actually happens to be a bend-in-sensitive B3 fiber. It has a slightly different core size. So when you're testing from one direction to the other, you're going to have a loss in power, and the other direction, a gain in power. So in this direction, I have a gain in power because I'm going from a smaller mode field diameter to a larger. When I have a gain in power, I'm going to have a negative value. So this is a gainer. Looking from the opposite direction. So looking from this opposite direction here, I'm going to have a loser. So it's going to be an exaggerated loss because I'm going from a larger to smaller mode field diameter. You're going to see this a lot. The only way to accurately measure any splice, and in particular splices of dissimilar mode field diameters, is to take these 2 numbers and average them out. So we're really a lot closer to like 0.1 or 0.05 or something like that. I'm not doing the math today, but you get the idea. So anytime there's a mode field diameter mismatch, that's going to happen. So now this explains what we're seeing here. Is we're seeing a change in fiber type. So if I zoom into that a little bit, you'll see how our power goes up. Gain in power, loss in power. So we have a gainer and a loser. So I put that in there just so we can, just so we can have something to look at. And I also like to draw Batman. And so essentially that's our, the interpretation of that. So that ties into the 101 stuff, right? But you can clearly see both events. These are only 10 meters apart, right? So is it 10 meters? Yeah, something like that. 10 meters. So 9.4 meters. So about 30 feet of fiber here, right? I can clearly see them. I can clearly distinguish these 2 fibers difference from each other, but I'm using 5 nanoseconds. 5 nanoseconds. 5 nanoseconds is good to about 10 miles or so if you're lucky. With a higher averaging time. Let me go to 50 nanoseconds. Longer pulse width, I can test further. Let's see how that looks at 50 nanoseconds. So it's going to go in there and shoot the exact same fiber, and then we'll see what it looks like now. And once it traces flat like this, all you're doing is wasting time. So if you have it set for 60 seconds and 15 seconds in it's flat, then you're wasting, the rest of the time. So in this case here, that's, if I highlight event number 2 here now, zoom into it, we now have this thing, you see the symbol over here, this means merged event, meaning it sees 2 events. So it can see the first peak, it can see the second peak, but it cannot see the noise floor. And so what's happening here is it's saying, hey, you know what, I can see where we have reflection because it starts to go up. And here's the top of the reflection for the first fiber. So it's the top of the mountain of the first fiber. And then we see another reflection here that juts out, but we don't see the noise floor, which is down here. We can't measure loss if we're not at the noise floor. This needs to come all the way back down here to measure it. So now it measures it as one whole event, 0.264. This is a merged event. It's also merged not just from resolution, but also from pulse width. From dead zone, which is what I'll talk about next as it relates to pulse width. So that's the first issue with pulse width. As you increase pulse, you test further, you sacrifice the resolution, what you can see close up to each other. Another issue with pulse width, I'm going to go back and I'm going to leave it there at 50 nanoseconds. I'm going to select this event right here, number 4. This event number 4 here is a UPC connector that I have mid-span. And so because I selected it and hit this button to the right, if I go up here to the top where it says measure, this will turn on my markers. It'll turn on the markers that were used to measure this event. So the distance between A and B is 23 meters. That's my dead zone, 23 meters, right? If you want, we can break this down into Merca here, and we can go to where is it at? There we go. Go to Merca here, and change it down to footage. So this between A and B is 76 feet. 76 feet here, right? What this means is when the OTDR pulse hits that connector, it blinds itself for 76 feet. It knows what the power is coming into the connector. It knows what the power is coming out of the connector. It doesn't know what's in here. Is there 1 splice, 2 splices, 3 splices? It doesn't know. It just knows what it looks like going into the dead zone, and it knows what it looks like coming out of the dead zone, right? It just doesn't know what's in there. And so that's at 50 nanoseconds. Now, if I drop this down, if I go back to OTDR here and drop it down to 5 nanoseconds, and then we retest that, at 5 nanoseconds, I'm going to have better resolution, but also lower power. So here's what's happening. As you increase your pulse width, you increase your power. The more power, the higher the total power coming back from a reflection. The percentage doesn't change. It's just the input power changes. Meaning, if I'm shooting something out of 20 dBm and my reflection's 4%, I'm going to get 4% of 20 dBm, which is a lot of power. If I shoot it at neg 10 dBm, it's still 4% power return, but it's 4% from minus 10 dBm, right? So the total power reflected is not as bad. So as you increase your pulse width, you get more total power reflected coming back, which means it affects your dead zone, or the area of the fiber you're blind to. It's like you come around a corner and there's high beams on, you look at the high beams and you can't see for X amount of seconds. That's dead zone. The brighter that high beam, the longer it takes for you to adjust your eyes. The OTDR is the same. So we went from 76 feet to, select event number 5 there, and then we'll go to measure, 76 feet to about 31 feet. So we've cut our dead zone in half, because the last one, if you picture the last one, it went like this, right? It came in and went up and it came down right around here. So we've recovered all of this right here for visibility. This is a huge issue. After every single reflection, you are going to have dead zone. And this is really important to understand, because when you are sitting inside, say, a switch or a hub, and you are sitting at an FTP panel, if you're sitting at this FTP panel with all these individual ports, and when you plug in your OTDR into this particular panel and test, it is not uncommon for you to have a splice. You could have a pigtail splice right here. You could have a vault splice here. You might even have a splice before that transitions from inside plant to outside plant. So all of a sudden you have this fiber that comes in through there. So what's the distance between these? So typically, and this will vary, right? A pigtail splice is going to be close. We're talking a couple of feet here. So 2 to 3 feet. Usually it's too close, it merges into the connector. So we have 0.5 dB max from the connector itself, from the FTP panel. We're going to have 0.1 from the pigtail splice. And then another 30 feet away, we have a transitional splice. Going from your from inside cable to outside cable, that's going to be another 0.1. And then we have our vault. That could be 150 feet away. And the vault splice is going to have 0.1. If you set your pulse width to 5 nanoseconds, you're going to see this, and you're going to see this. And of course, you're going to see this, but it'll be merged with this. And so your patch panel will say 0.6, and you scrub and scrub and scrub and scrub. Well, that 0.6 includes the pigtail splice. We're starting to see some companies actually increase their patch panel loss to assume that there's a pigtail splice nearby. Particularly for some of these pre-terminated panels. So at 5 nanoseconds, that's what we see. Now, if you scoot over to 275 nanoseconds because you're testing further, you're basically at 275 nanoseconds, you're going to have this. You're going to have this here on your launch. And so if you zoom into the launch, which we'll do in a second, you're going to hide all of this. All of these losses will get sucked into the connector loss. And so now all of a sudden we're looking at, a loss, your launch, because of course you have a launch cable here, right? So you're able to measure this connector. And so now all of a sudden you'll have, basically 0.8 dB of loss at your connector. And you'll scrub that all day long and it's never going to get below 0.5 because this is merged. So this is the advanced part of, and so what do? You do a short shot. You shoot something at 5 nanoseconds, you shoot something at 275. You want to see what's up close, you want to see what's far away. And that's what's happening there. So hopefully that makes sense. But so that's why it's important to understand pulse width and all of that, because that really affects it greatly. So how do you fix that? Well, several things. One, use a launch cable to push your panel away from you. If you use a 3-meter pigtail and plug it into an FTP and test, you're going to merge that FTP into your OTDR and you won't see the loss at that FTP, which is not good. Use a launch cable and you push it out. You also balance it with duration. So this is what an OTDR trace looks like. I'm going to shoot real time. This is what an OTDR trace looks like in real time. This right here, it's just noise. And of course, going through VNC and across the internet here, it looks like it's probably just stumbling. But this is actually real time to me, and I can see it. It's just moving like crazy. Only noise moves in an OTDR trace. Because if you look at it here, there's this, you can see my reflection poking out here, But you don't see any of these losses, these low loss stuff in here because they're lost in the noise floor. But only noise moves. So if I were to open this back up, you'll see that those reflections don't move much. They shift a little bit, but they're there all the time. Everything else around moves, right? So, to kind of give you something a little bit more stable. So here's 10 nanoseconds. Here's 30 nanoseconds. As you increase your pulse width, your real time starts to flatten out better. And so that's what it looks like in real time. And so at 10 nanoseconds, this is what it looks like. Well, how do we get from this to a flat trace? That is using duration. We have a 4 Hertz analyzer. So we analyze movement 4 times a second. Every time something moves, we flatten it. It moves, we flatten it. We move, it flattens it, right? Until it smooths out. So as you increase this, you can decrease this, right? Or inversely, if I increase this, then I can decrease this. So this is a balance between resolution and time. If I'm testing an 864, I want an 864 to be as quick as possible. In fact, right now, 864 splices, a good splicer can do an 864 splice in about 7 hours. An 864 butt splice ribbon in about 7 hours with a good machine and a good setup, about 7 hours. It takes over 20 hours to test it. It takes much longer to test it than it does to actually splice it these days. That's once you're sitting down and splicing. It takes about 7 hours, roughly. On average, we're probably seeing it closer to a day and a half because of logistics, but ideally it's about 7 hours. So you want to optimize your time, but you don't want to sacrifice your visibility. So you have to juggle the two. In a maintenance situation, I want the best resolution possible because I want to see as much as humanly possible. So in a maintenance situation, I want my pulse width to be as low as I can get it at the expense of time. Because if, the difference, for me in a maintenance situation, the difference between 5 seconds and 90 seconds is not huge compared to the time I'll waste in fault isolation trying to find something by driving around because I pinpointed the wrong place. So at 3 nanoseconds, so I'm going to set this for 3 nanoseconds here. So it's going to be 3 nanoseconds at 90 seconds. I'm going to hit start average. It's going to run through and run it and do a quick trace. And so we'll watch it. As time goes on, you'll see it'll get flatter and flatter. But at some point, it won't improve at all. it'll just stay noisy. Of course, this is a fairly short span, but at 3 nanoseconds, it would be noisy mid-span all the way to the end. If it quits moving, if the noise doesn't improve, in fact, you know, I'm gonna add some loss in here. So I went and added some loss in there. So I'm gonna retest this, and I know we're getting close to the end of time here, so I'm gonna kind of wrap it up here a little bit. But so basically, what happens here is, so I had a little bit of attenuation just so I had some loss. So I added attenuation to simulate length, and so as it runs through, it's taking longer and longer and longer for it to clean up. But at some point, it just stops cleaning up. And so that means I have to increase my pulse width. So as you increase your pulse width, you can decrease your duration, right? So normally what I do in a maintenance situation, with newer OTDRs, auto mode works really well if you have a good launch. Very critically important, because we have much better processors than we did in the past. So normally what I would do in a maintenance situation is I would set my durations for, say, 90 seconds. Over here to the right, we have this auto button. And I know some people rolling their eyes, auto button. This works pretty good. And then I'll select both wavelengths in case there's any pinching in the fiber. I will set it for 90 seconds. When I hit auto, it's going to auto the lowest pulse width that it can use based on a 90-second trace for that fiber, right? And so I'm not going to do 90, I'll do 30. Just so we're not sitting here. So what is the best pulse width at 30 seconds? So you see the range and pulse width grayed out. So I'll start averaging. It's going to go in there and tell me, hey, this is the pulse width that I prefer. And then, of course, from here, you can tweak it down. So normally what I like to do is I like to set an average. Do the initial test auto to let the OTDR narrow down the settings. And then I'll tweak it from there. So, you know, you can see my big pinch there. So it's saying, you know what, 30 nanoseconds is the best. 30 nanoseconds is the best pulse width to use at 30 seconds, right? And so I'm going to go ahead and stop that. And, you know, that'll give us a nice clean trace. But what's the best pulse width at 5 nanoseconds? Because time is really important to me. So I'll auto it at 5 and hit start average here. And it'll go in there. And then what is the best that it can do at 5 nanoseconds? So the last one was 30, and then this one is 50. So you'll see how decreased duration, it's got to increase pulse width. And so this is what's happening here. So at 5 seconds, this is the best that I can do. And then, of course, you know, you can see macro bending here. So at 1550, event number 4 here is 2.5 at 1550. At 1310 here, at 1310, it is 0.6. Much better. This is macro bending because, you know, the longer the wavelength, the more issue you can have with pinching, which is more of the fiber 101 stuff. But that's how I set an OTDR. So you got to make sure your range is right, your pulse width is right, and your duration is right. You kind of tweak that. So to get more precise, though, this is when you get into your test configuration and you adjust things like index of refraction. So this is the speed of light within the glass. Adjust this for that specific fiber type that you have. So if you have one for leaf fiber, have one for true wave, classic, have one for SMF28, whatever. This will give you more precise fault isolation, is what that does. And so, you know, that'll get you closer. What I normally like to do, for instance, what I like to do to get more precise fault isolation is event number 4 here is 1,587 feet. And I know where this is at in the network. I know exactly where it's at in the network because I know my network. I have a network diagram. At 1,587 feet is that one connector at that pass-through hub. You can go to that. If you know the sheath distance from where you're at to that location, you can adjust the index of refraction until your sheath distance equals this. And now you're shooting sheath footage rather than optical footage, you know, which has that index, which has a helix factor or a twist to it. And now you get more precise. By adjusting your index of refraction, you can convert your optical footage to your sheath footage. And so if your prints have the sheath footages for your OSP cable, so when I was a splicer, we would write down the sequentials on the cable. And if you have a critical span with a critical customer that has SLAs like governmental work or whatever, 911, you can go to one of these spans. Let's say we had a splice here and a splice here. I could access both of these splices physically, crawl into this hole, read the sequentials, the numbers on the cable sheath, you know, read the sequentials on the cable sheet, you know, give me a number here, it'll give me a number here. I can shoot the OTDR trace, change the index of refraction until the distance between here and here equals the sheath footage that I got. And then now you're shooting sheath footage for this whole thing. That's more precise fault isolation. That's something that you can do proactively more. If you're in a metro environment and you really can't pinpoint where the damage is at, you can adjust the index for refraction to compensate for that, right? And so that allows you to do that itself and, get a little bit more precise. So this is how you adjust these three settings along with index of refraction to really optimize your setting. And it's really critically important. And the trick for these three here is to get them as low as possible. The only subjective thing is duration. How much time do I have? If I'm pinched for time, then I reduce the duration. If 30 seconds or 45 seconds per fiber doesn't affect me, then shoot a longer time because you'll get a better pulse width, a better resolution. And most of y'all, if you're doing circuit testing or quick turn-up testing, and it's only 2 fibers, 4 fibers, an extra 5 minutes is not going to kill you. If you're doing an 864, an extra 30 seconds per fiber is going to chew up an entire day of labor. And so you have to kind of balance the two. In a maintenance situation, you do that. This is why IOLM is really cool, because I'm sure you all have seen IOLM, because IOLM allows you to, it's really good for maintenance situations where you can get in there and basically just run an auto test. So IOLM, you set up a configuration, you hit start. And it goes in there and it shoots short, long, intermediate pulse widths, and it stitches it all together. This is really good in a maintenance environment in particular, because it'll always show you something at 10 feet, 10 miles, and 100 miles. If you got an OTDR, do 100 miles. And essentially all you do is just hit start, right? Hit start, it'll go in there and do its test, run through and do its test. And then once it's done, it'll reveal the information. And so I'll let it run, and then I'll do a quick recap. So really the big takeaways for advanced OTDR is to understand that, we have different settings within the OTDR. And the primary ones that we really care about is pulse width, and range or distance, and duration or time. And it's important to optimize these three. Pulse width is really the one that you really need to nail down. Range is kind of a no-brainer. Am I seeing everything that I need to see range-wise on the fiber? Can I see the beginning? Can I see the end? Can I see the middle? Whatever, right? That's range. Pulse width, again, the shorter the pulse width, the better the resolution, right? The better the resolution. And so you really want the best resolution possible. But the problem with very short resolution is you contribute noise to the trace. So if you have 0.05 dB splice losses and stuff like that, they may get hidden in the noise of the OTDR trace. Because you have this OTDR trace at 5 nanoseconds. If you zoom in, it might look like this. At 100 nanoseconds, it'll look like this. And so we will lose a low loss splice inside of these valleys. But do you really care about a splice loss that low? Or if you're looking for more higher contributing stuff? So that's where you balance the resolution versus, the quality of the trace. So the shorter the resolution, the shorter the pulse width, rather, the better the resolution. They do contribute some noise, and you lose some distance, right? And so you get, better resolution at the sacrifice of distance. But that means you have less distance, right? And if you got a higher resolution, you can see further, but the spacing between your stuff is not as good. And you compensate with it with duration. And that's what duration allows you to do. Is it gives the OTDR trace time to clean up from this to this. And so this is 5 nanoseconds at 5 seconds. This here is 5 nanoseconds at 30 seconds. And so are you willing to wait an extra 25 seconds for an improved quality of a trace? And the answer should be yes for most of your stuff, in most cases. And so when we go back to this IOLM trace, it's done. So IOLM, we always see something close up. So here's this LC connector here. So you see the 150, here's my launch, 150 meters. This is my gainer for my LC connector. This is the other side of that LC connector 10 meters away. And then we have, this is actually not a splice. This is a really good APC connector. If I drop this down and say, and it tells us here too, if you look at it, it says, make sure this splice is, make sure you properly splice it, or this could be a really good APC connector. And this is actually a really good APC connector. So that passes now. And then we have over here where it says, hey, you have a pinch. You pinch the fiber, and that's that knot I tied in there earlier. And so that's IOLM. So basically that's kind of precise fault isolation in about an hour. Hopefully a lot of that makes sense.
But thank you, Kevin. Appreciate all the really good information. This is very helpful.
Yeah. I mean, give us, if it's positive feedback, send it directly to my boss. If it's negative feedback, you can send it to me. But, I know it's 1 hour. I kind of it feels like a lot of information, but the assumption is that you all are running OTDRs, so hopefully we covered some in detail some things that you haven't thought of, or a refresher for some of you, and we will follow up with a recording of this video and a lot of additional like job aids, 2-pagers, how to set up your OTDR, how to set up IOLM, how to set up OLTS, and a bunch of little 15-minute videos that are also the same, to kind of reinforce a lot of that. And you'll have my contact information, of course, Morgan's. Feel free to reach out to us. We're here to support you. And so we thank you for your time, and hope you have a good weekend, I guess, because it's Friday.
It's Thursday.
Oh, it's Thursday. I'm taking tomorrow off. I'm gonna take tomorrow off. So it's Friday for me. So
Thursday for everyone else.
Good deal.
All right.
Thank you very
Thanks,
much.
everyone. Appreciate your time.